using conservation of momentum, we can actually talk about rocket propulsion. Now, rocket propulsion, there's a lot of misconceptions dealing with how rockets work. Imagine a rocket on a launch pad, right? You've probably seen space shuttle launches or rocket launches like SpaceX, where a huge amount of fuel is ignited, causing a great amount of thrust coming out of the back of the rocket. That rocket then lifts off the ground and flies off, hopefully, into space. Many people think that the reason the rocket moves is because the propellant is pushing off the ground. Kind of like if you're sitting on a wheeled chair near a wall, you push off the wall to move. But that's actually not what's happening. Yes, the propellant is hitting the ground, but that's not what's pushing up the rocket. What's pushing up the rocket is the propellant itself. It's a conservation of momentum problem. So imagine, for instance, you're trapped on a frozen, frictionless lake. All around you, right, again, imagine a super icy lake. It's technically frictionless, although ice is not frictionless, let's pretend it is. You're trapped in the middle of this large lake. How do you get from the middle of the lake to one side? You can't walk. Walking requires friction. How do you move? Well, one way to do it, you could take off your cap, throw it in one direction. The momentum you impart, imagine that's like a collision or explosion. You throw your cap in one direction, imparting momentum on that object. You are pushed in the opposite direction. How much depends on your relative weight. Of course, your cap doesn't weigh nearly as much as you do. So, and how hard you throw that cap also determines how fast you slide backwards. Now, you might have experienced it if you ever tried to throw a medicine ball or something heavy, right? You shove it with all your might, but you can feel yourself get pushed back. What a rocket does is it accelerates fuel out the back. Since this fuel is leaving with some velocity, it has momentum associated with it. Every time this rocket throws out a little bit of fuel, it's the same result as you throwing your hat on that icy lake. The rocket goes in the opposite direction. Conservation of momentum. Before this is ignited, the rocket and the fuel in the rocket have no momentum. There's no velocity. But once you impart the fuel with a negative momentum, a momentum in the negative direction, the remaining fuel in the rocket moves in the positive direction. So rockets work in the depths of space when there's nothing to push off of as far as the fuel is concerned, or when they're sitting on the platform. Again, the rocket isn't pushing off of anything. The rocket is being propelled by the fuel it spits out. Now, that leads to a problem. Rockets can't work for an infinite amount of time. They have a limited fuel supply, and when that fuel supply runs out, the rockets can't accelerate anymore. So you have to make sure you bring enough fuel with you to do what the task you need to do. Fuel itself has weight. So the more fuel you bring, the more mass of the rocket, and the more fuel you need to launch that rocket. So fuel itself has mass. So that leads to a compounding problem that you have to launch a bigger rocket, you need more fuel, and more fuel gives you a bigger rocket, which you need more fuel to launch, and so on. So you actually use a lot of fuel to launch these rockets. So the acceleration experienced by a rocket, we won't derive this, your book just sort of gives it to you, as will I, is given here. Where the acceleration is the upward acceleration the rocket experiences, and it's dependent upon a few different things. It depends upon the velocity or the speed the propellant is ejected. The faster you can spit out that propellant, the more momentum you give that propellant. The more momentum downward you give that propellant, the more momentum upward your rocket gets. So the faster you can spit out that fuel, the better. And by faster, I don't mean dumping all your fuel at once. I mean the faster the speed you can get those particles coming out the back end of your rocket, the better. It depends on how much fuel you burn, right? The delta M is the mass of the fuel. The more fuel you have to burn, the better the acceleration of the rocket. the acceleration is inversely proportional to the mass of the rocket. The bigger the rocket, the slower that acceleration. Again, it's like trying to speed up a car versus a school bus. A school bus has more inertia, more inertial mass, therefore it's harder to accelerate given the same amount of force. And then finally, inversely proportional to how quickly you spit out that fuel, right? If you want a massive acceleration, then you have to dump your fuel quickly. If you want a very slow, gradual acceleration, then you can be conservative in your fuel use and burn it slowly. And then finally, for rockets on Earth, of course, the acceleration of the rocket depends on g, where you subtract the acceleration due to Earth's gravity. In space, g is 0. If you're far enough away from a planetary body, g is effectively 0. And the acceleration just depends on these 4 terms. But most rockets we launch are on the Earth. So the acceleration, the Earth's gravity fights that acceleration. Which gives you an interesting minimum, right? This term here, this first 4 terms together, has to be greater than g or the acceleration is 0 or negative. So if you want liftoff, you have to make sure this part of the acceleration is greater than the force of gravity downward, or the gravitational acceleration downward. Imagine firing a rocket that's incredibly weak. The rocket just sits there, you see a little bit of fuel spit out the bottom. The rocket might be a little lighter. If you had a scale measuring it, it might be a little lighter, but it's still not moving upwards. So to make a better rocket, NASA is looking for designs that try to maximize this equation. And one of the drives they've come out with is actually called an ion drive. It's fairly cool technology. What an ion drive does is it doesn't burn fuel like in the traditional rocket. It's not a chemical process where hydrogen and oxygen are brought together and incredible temperature causes the flames to shoot out the back of the rocket, sending the propellant downward. What they do is they use a little particle accelerator basically and accelerate ions to very high, or charged particles, to very high speeds. And they spit those out the back. So rather than having gases coming out at a few thousand meters per second, they can spit out particles at substantial fractions of the speed of light. That is an incredibly high velocity, which means that gives them a good acceleration. The problem is delta m, the amount of mass that they can spit out in some unit of time, is very small. One advantage of rockets and the chemical process of burning solid fuel and liquid fuel rockets is that you can burn through your fuel very quickly, which of course gives you a very big acceleration. With these ion drives, the ion drives aren't powerful enough to lift a rocket off the Earth. But if you're already in space and you don't have to worry about this minus g term, then you'll get acceleration as long as you, even if the mass is small, as long as the speed of propellant is high, you'll get acceleration. Because the ions are ejected at such a high speed, you don't have to use very many of them at a given time to get an acceleration, which means that you're more efficient in your fuel use. So these ion drives sip fuel rather than gulp it down to move the object forward. But the accelerations they produce are small, but they will last a much, much, much longer time. So in the future, ion drives might be something that NASA regularly uses in deep space missions.